Okay, good evening, good morning, Professor David J. De Los Reyes. It's August 14. The time is 1:34 a.m. August 14, it's Monday morning already. Okay, my topic for this morning will be a long video format discussion, and this is on alternating current circuit. So for those of you who are following my long video format discussion on alternating current circuit. This will now be lesson number 18. Okay, let's proceed. Or 19 rather. Alternating current circuit, lesson number 19. Uh, Actually, this will be my second lecture on power factor correction. But since I want to emphasize the importance of power factor correction, so I will be giving you a practical problem in which every household here in the world could use this concept here on how to improve the power factor of your house or business, and actually to minimize your total power bill from the utility companies. Okay, let's proceed. So the title of the topic for this morning will be power factor correction example problem. Uh, every household could use this concept on how to minimize your utility bills. Okay, this is with regards to the so-called power factor correction. Mr. Elon Musk is selling a gadget online in which to improve or lessen our current consumption, and this is actually the concept behind it. Okay, this is the concept behind it. It is just power factor correction. We are just eliminating the reactive power, okay, consumed by the motor loads. Okay, we are just minimizing or totally eliminating the reactive power consumed by the motor loads for the total current drawn to be minimum, or you could actually save from your utility bill. Okay, let's proceed. The given example, the total lighting loads will be 12 kilowatts. That's lots of loads. So this could be, like an example, this could be the casino maybe, the total lighting load for a casino. They are using LED or some alternating current bulbs maybe. The total is 12 kilowatts. That is just for an illustration, okay? So we are given a business or household, maybe the total lighting loads is 12 kilowatts. That's flats. Total motor loads, 20 horsepower. It's not so many because if it's a business company involving motor loads, it's not only 20 horsepower. So 20 horsepower could be maybe a high value household maybe. So the total motor loads will be 20 horsepower. The power factor is 60%. Of course, it is lagging because it's motor loads, right? The problem is asking what will be capital letter I with the subscript old, meaning the old total current. Capital letter S with the subscript old, meaning the total old apparent power. Okay. PF with the subscript old, meaning the old power factor. The old power factor is not 60% because this 60% only refers to the motors, okay? Because we got a lighting load. So this 60% is not the old power factor. Okay, next one. Capital letter I with the subscript new, meaning the total new current. Number 4, capital letter S with the subscript new, the total apparent power. Number 5, the kilobars with the subscript C, meaning what will be the kilobars of the condenser needed to be connected in parallel with the system such that the resulting power factor of the system, okay, the overall, after the connection, it will be unity. So meaning we are expecting a 100% efficiency. Okay? Okay, let's try to bring out the figure. The figure will be something like this. Of course, the connection is parallel, right? The light is stuck to the utility line, the motor loads is stuck to the utility line, and the condenser needed to correct the power factor to 100% is must be also connected in parallel. So actually we are considering for the meantime parallel impedances or parallel loads that are connected in parallel. Okay, and the applied voltage is 120 volts. It seems we are in the USA, and the frequency is 60 Hz. Okay, let's try to bring out the solution. To bring out the solution, we start with the lighting load. Okay, the lighting load, if we try to draw the power triangle of a lighting load, okay, normally a lighting load is, a power triangle is actually a triangle, right? Normally that's a power triangle. But for a lighting load, instead of a right triangle, the power triangle is just simply a straight line. Because it got no inductive load, it got no capacitive load, so the resulting triangle is just simply a straight line for a lighting load. Okay, that's normal or that is standard. You cannot change that one. If the load is lighting load, the power triangle is just simply a straight line. So P1 here is equal to 12 kilowatts, and that is actually same as S1. S1 also will be 12. It should be kVA. Because P1 and S1 will be equal when the load is lighting. Because the power factor for a lighting load is actually, equal to 100%. If your lighting load is 100% power factor. So it seems the lighting load is with the power factor 100%. And the motor loads, what is given is actually the power factor is 60%. So, okay, so this is 100% and this is 60%. And one of the conditions is the problem is asking for the old power factor. Okay, because we need to know the old power factor for us to increase the power factor to unity if it's needed to be increased. Okay, for the motor loads, the true power consumption of the motor loads is actually 20 horsepower, right? So true power with the subscript 2, meaning for motor loads, it will be 20 horsepower. We convert horsepower to watts, so this is multiplied by 746 watts per horsepower. So this horsepower here cancels. What remains is watts. But I want to convert this watts to kilowatts, so I will be multiplying this right hand side by 1 kilowatt per 1000 watt. So this watts here cancel with this. So the overall unit of the right hand side will now be kilowatts. Okay, performing the operation 20 times 746 divided by 1000, that will be 14.92 kilowatts. Okay, so the true power consumption of the motor loads alone is 14.92, right? The given power factor in motor loads is 60%, so PF will be 0.60. But one of the definitions of the power factor is, what is one of the definitions of the power factor? It is the cosine of angle of theta. This should be old. This is theta 2. Theta 2 refers to motor loads, right? So power factor number 2, okay, as per definition, it is cosine of the angle of theta 2. Since we are given power factor number 2, it is 60%, right? We could compute for theta 2. We could compute for this angle here, right? So taking the arc cosine of both sides, the arc cosine of theta 2 will be theta 2, and the arc cosine of power factor number 2 is the arc cosine of power factor number 2. And this should be the arc cosine of 0.60. If you try to bring out your calculator, okay, you press 0.60, second function cosine. The angle should be 53.13 degrees. So meaning to say, if the power factor of the motor loads is 60%, this angle here is 53.13 degrees. So if we need to compute for Q2 and S2, okay, we could compute now because we are given P2 and we are given this angle, right? So to compute for Q2, the relation of Q2 with respect to P2 will be tangent, right? So tangent of 53.13 degrees will be Q2. The reactive kilobars of all the motor loads all over the true power consumption of all the motor loads, that is Q2 over P2. Solving for Q2 will be, we cross multiply, right? P2 times tangent of theta 2. We cross multiply. So this will be 14.92 tangent of 53.13 degrees. Tangent of 53.13 degrees, it's more than 1 because it's greater than 45 degrees. It's 1.33 times 14.92. What comes out is 19.89 kilobars. So the reactive volt amperes of all the motor loads is 19.89 kilobars. It's very big. And this contributes to the high current usage. If we could eliminate this one to lessen our current, we could lessen it. Okay? So combining the power triangle number 1 and power triangle number 2, it should be a vector addition, right? Power triangle number 1 is this 12 kilowatts here. So we are adding the real power and the so-called imaginary power, right? Load number 1, the true power is 12 kilowatts. The motor loads, the true power is 14.92. Real power, right? We take the sum, the total will be 26.92. Okay? The kilobars of all the motor loads is 19.89. So actually, what comes out if we try to combine the total lighting loads and the motor loads, it's a big, okay, right triangle. So actually, the total apparent power of the system is actually very big, 33.47 kVA. That's large, right? Why I got 33.47? Okay, the total of 12 plus 14.92 is 26.92. The adjacent side, considering this angle, is 26.92. This is 19.89. So we use Pythagoras principle, right? 26.92 square, 19.89 square. We are solving toward the hypotenuse. The hypotenuse is actually the total apparent power consumption. So what comes out? I perform this one inside the calculator. That will be 26.92, okay, square plus open quantity. I will square again this one. 19.89 square plus quantity equals, take the square root. The value is 33.47 kVA. So if you are on the board exams, you don't have to show the simplification of this. Just perform this one inside your calculator, but make sure it is correct, because if it is wrong, you're wrong, right? So the all total apparent power is 33.47 kVA. It's very big, okay? And to lessen the current consumption of your house or your business, you must have to decrease this one. And to decrease this one, we must have to eliminate this portion here, this one. Okay, we must have to eliminate this. Because if we could eliminate the opposite side, what comes out will just be simply a straight line, and a straight line is actually less than the hypotenuse. So actually, if we try to eliminate this one, connect a capacitor in parallel with the system. Put a Q sub C, in which the value of Q sub C will be 19.89 kilobars. Okay? to eliminate this big 33.47 kVA, you kill this one with this, right? So this is upward, this is downward. What comes out will now just be simply a straight line, right? So the total real power is actually less than the total apparent power, because the total apparent power is actually the hypotenuse. We eliminated Q2 because we connected in parallel with this system a capacitor in which Mr. Elon Musk is selling online. The gadget Mr. Elon Musk is selling it's just a pure capacitor, right? That is for power factor correction to lessen the total apparent power, okay, consumed by our system. Okay, so the total apparent power is 33.47 kVA. Okay, let's try to compute for the old current. Apparent power is actually S, and it is actually EI, right? So if we know S, we know E, we could compute for I, right? So I will be S over E. Okay? So the old current, which is very big, will be 33.47. We convert this to volt ampere, so this will be multiplied by 1000 over 120. The all total consumption of your system, of our system, is 279 amperes. That's big. Oh, that's not so big. For this example, we call it big, right? Because if your consumption is megavolt ampere, okay, it should be 1000 amperes. It's not only by 279. So the current consumption, okay, with these given conditions, right, it is 279 amperes. And if we try to compute the old power factor, we will try to see if it's really effective or not, okay. Power factor with the subscript old, meaning the old power factor will be the old true power all over the old apparent power times 100%. The old power is actually 26.92, and the old apparent power is 33.47 times 100%. And if we try to divide this, the power factor of the system overall is just 80.43%. Okay? 80.43 is a little bit high, but if you could raise this one to 100%, okay, your utility company loves you, okay, because you are helping them decrease the current consumption of the system, right? So to raise the power factor from 80.43% to 100%, we kill this 19.89 kilobar, okay, by connecting a condenser in parallel with the system. This is the condenser, right? So the resulting power triangle now, okay, the existing kilobar is 19.89, and we will kill this one by connecting a condenser with the value equivalent to this, right? So if they are equal, the kilobars will be gone, right? So our power triangle will just be simply a straight line. So this straight line here is actually less than the original hypotenuse. Okay, so S nu now will be P nu over power factor, right? So this should be 26.92 over 1. And the new apparent power will be 26.92. Okay? If we could kill the 19.89 kilobars, the total apparent consumption of the system will just be simply 26.92 or almost 27. Originally, that was 33.47 or 34. So actually, that was less than 7 kVA. It's not so many current, but it was less, right? So if we try to compute for the new current, it will be this new kVA over 120, and what comes out is 224. So 279 minus 224, that will be 5, okay? So the current consumption is actually less than 55 amperes now. It's not so big, but what you call this, it increases our power factor to 100%. That's why I told you, if your power factor is 90%, your utility company loves you. Right? And the new value Q sub C, it will be equivalent to the original Q sub QL, or the reactive power of the motor loads, 19.89. So for the kilobars of the capacitor, okay, I place it here. The designation for reactive power consumption is Q. So capital letter Q with the subscript C, meaning the reactive power of the needed capacitor should be equal to the original 19.89 kilobars. So this will be our answer for the kilobars. So if you know the kilobars of this, okay, if you know the kilobars, kilobars is actually I squared times X sub C. So if you know the current, you know the kilobars, you could compute for X sub C. Okay, you could compute for X sub C, and this should be 1 over 2 pi FC. Right? So if you know X sub C, you know the frequency, we can compute for the required capacitance of the needed condenser. Okay? So if you buy it from Amazon or online, you could specify the capacitance of that condenser, okay, and you could buy it. Okay, that's the reason why the problem is asking for the kilobars of the capacitor. Because upon knowing the kilobars, okay, we know the current, we can compute for X sub C, and by using the formula X sub C equal to 1 over 2 pi FC, we can compute for the capacitance of the capacitor or the condenser needed to raise the power factor to 100%. Okay, that's it. That's a practical problem in which every household in this world could use it to improve their, what you call this, power factor, and actually you could minimize your, okay, utility bills. Okay, so for those of you who are taking up electrical engineering, this is for you. If you want to subscribe to my channel is at youtube.com/@ProfDavidJ.De. If you want to share it, please click share. Okay, so for those of you who are taking up electrical engineering, please watch my long video format discussion on alternating current circuit. I am assuring you, you will learn something from it. Okay, good morning from Los Angeles.